So I was finally able to render text to the screen, and I'm going to try to explain the whole process, everything that I went through, and the challenges and how I solved them. And I might be all over the place because there's a lot of stuff to explain. But I'm gonna wait to see if it's streaming first. I'm really happy about this because it took me a massive amount of time to figure this out. So hopefully this is gonna help people. And the challenge was to render 2D text into a 3D visualization. So I want to give a shout out to uh, this guy here. He helped me just now today at the end with this technique called billboarding, which is making the quad always face the camera. I'm not gonna explain the functionality from OpenGL. I'm just gonna talk about the overall process. So if you don't know that, go search somewhere else. And I also want to give a shout out to scratchpixel because it helped me a lot. And I read specifically this here is a very good one. I read this a bunch of times already, and also to Raylib. So the final approach, the last approach that I tried was to use a Raylib example. And that I found, I think on their repository, and then the text wasn't showing, and I didn't know why. So I think I'm gonna step over the code from Raylib. But pretty much the way that it works to render text is actually very simple, the overall process, the pipeline. So you start with a TTF file, which is a file that is gonna contain information of how to render fonts, or the information for the font. And all that a font is, on the TTF format, is just a collection of Bezier curves. And Bezier curves are curves that have the beginning point and the end point, and then they have one or more control points in the middle. And the control points are going to be the things that dictate the curve of the Bezier curve. That makes sense. So I think I draw on Scaly Draw here. So it's pretty much like this. And then depending on where you put this, then it makes the shape of the curve. And this is just a polynomial equation. And then based on that, you can create any format you want pretty much. So the TTF file is going to contain all the information that is necessary to create these vectors that represents the characters. So what you're going to do is read the file, the information from the file, then parse the information and store on a struct all the stuff that is necessary to create an image out of the vectors. And the image is going to be a texture on OpenGL. And the way you create the texture is going to be based on the information you extract from the font file. And in order to extract the information, usually you're going to use a library because it's very annoying to do it. And the way that Raylib does it is with a library called stb_trueType, which is a header library, one header library. It has a bunch of functionality to do this stuff. And then they store the information on the struct. Then later on, you're going to create a GL text image, which is an OpenGL function that allows you to create an image on the, I believe, fragment shader. So it's very similar to the way you create buffers to put the data for the points. You create a space in memory that has the information for the image from the OpenGL side. Then you send the data that you extracted using a library. And then you use the information from, so you're creating one image that is going to contain all the characters, which is a font atlas. And that's the image you create on OpenGL. So that creates a buffer, which is a place in memory that contains that image. And then what you're going to do is, based on the information you extracted, you're going to loop over the text you have. Then based on whatever character you have, you're going to use the information extracted from the file to get the specifics of how the image is going to look like. Because each character has different heights. Maybe I can find the image here. There's an image somewhere that shows that. You have these specific numbers that are going to demonstrate or they're gonna allow you to draw the text in a way that the line that all of them are relative to makes sense. Because, for example, G goes lower than the other letters, so there's a baseline and there's a bunch of relative positions and the amount you have to advance from one character to the next as well. So you're pretty much using that information to read the... And then you're going to create a sampler, which is another place in memory where you hold the information for the overall texture, which is the texture that contains all the characters. Then use something called texture coordinates, which allows you to, based on the information you extracted from the TTF file, to find whatever character is the current character of the text you're trying to render. And then it's kind of like you're slicing the font atlas, which is the main image, only based on the current character you want to render. And you know that based on the text because you're looping over the text. So after you do that, then this sampler, which is on OpenGL code, is going to extract the information for that character only, and it's going to allow you to render that. So you're using one image, which is the font atlas, extracting a part of the image that is related to the specific character you want to render. And then you're doing that each time, and then the final position is going to be the overall geometry, which is made out of the GL position points. And this part is the one that is very confusing. So the way that it works, there's an image that I found, I don't remember where. I think it's on graphics programming. Is this part still very confusing to me to understand, but it's getting more clear. As this image here helps a lot to understand. So that's pretty much what is going on. So the GL positions is the positions that make up the geometry, and the texture coordinates are the positions. So you can imagine this whole image here would be the font atlas, and each one of the squares would be one specific character. So you loop over the text, and then based on whatever the current character is, you're gonna search for the texture coordinates are gonna represent that character on the image, and then you're going to extract one of these squares here from this image, and then based on the GL positions that you are sending along with the texture coordinates, it's going to make up the geometry, and it's going to slap that part of the font atlas into the geometry. So in the case of the text is going to be a quad, which is 2 triangles. So the texture coordinates and the GL positions are being the GL positions create the geometry, which is the quad. And the texture coordinates tell OpenGL what part of the main image to extract in order to put on the quad you're rendering. That's the overall process. So I think I'm gonna go over the Raylib code. So initially I got an example from Raylib that they provide that wasn't working. So the example they provide, which is another challenge that you have, because you're rendering text using quad, the text is going to be on 2D, but the visualization is on 3D. So this becomes challenging because if you're going to change the position of the camera, then the text is just going to be like a slice of the visualization. So the other challenge is how do you make the text face the camera as well. And then based on the example that they give, which I think is this one, so the way that I'm doing now is I want to incorporate this on another project that I'm creating. So I was trying to simplify everything so I can create a class that I can use on the other project. So I stepped over this a bunch of times, and then I got the functions that I thought that were necessary for me to do it on this project here. I think I can show here. Yeah. So I can see that if I move, it works. And I also got the shade, I don't remember, no, I think the fragment shader I got from somewhere else, I don't remember where. But there's also different types, different ways you can render the image. One is using sign distance fields, and the other is just using the normal texture. And the way that it works with the sign distance field is just creating this distance from the point. So you're sending a point, and then you're creating a range from that point, which is pretty much this thing here. This texture function is the one that I was talking about, which is the sampler. So you create a sampler here, This is the place in memory of where the font atlas is going to be. So the texture 0 is the whole font atlas, which is the whole image with all the characters. The frag texture coordinate is going to be the relative coordinates inside of the font atlas that are going to represent the current character you're trying to render, because you're obviously rendering one character at a time. And then from this function, what it's going to do is just going to extract the information from the font atlas based on the frag coordinates for that character. And the alpha is just going to give one channel of the colors, because there's 4 different channels, red, blue, green, and alpha. So you only use alpha because it's easier, and then you can color with another color, which is this thing here. So this is what's going to set the actual color. This just sets the shape, let's say, which is just going to be the strength of the color. So if the alpha is less than 1, then it's just going to be more transparent. But this is going to represent the information for the character, and then you get the length at the distance from the middle of them, which is this thing here. And then you call this other function, which is a function that is going to calculate steps from that point to the middle, let's say, or from the middle to that point. It's pretty much creating a range from like an imaginary middle line, and then some boundaries. And then based on that, this move steps is just going to be the function that determines how the gap is closed from the outside to the middle, let's say. And this creates the strength of the texture, which is going to represent the character. So that's one way, and the other way is you just don't do this stuff here and just do the texture. This is another problem I was having with the Raylib, but for now it seems that it is working with the project that I'm using, so I think I'm just going to do with sign distance fields. But if you try to do, because the example that I got there, so this example doesn't work, which I'm going to explain, but then eventually I got this other example here, which is a 3D example, and then this example uses a font default, which is another fragment shader that they use. And if you try to use the fragment shader for the sign distance field on this one, then it doesn't work. So this example that I got is from this link here. So I just removed a bunch of stuff and just left the simple text here, because I was trying to understand how it works. And I'm going to go back to the beginning. So the first time that I tried was with this one, which is the example that they provide on Raylib. And one of the challenges, the first challenge that I had is to understand how are they rendering the thing, because what Raylib does is use a batch rendering system. So they have they have a file called RLGL, which is this file right here, which is going to have a bunch of functions that allow them to render anything. And it was kind of confusing, to be honest, because the way that they do it is that on the beginning, before they do anything, they're going to call a function on the init there that is going to allocate a bunch of memory to be used by the buffers later on the rendering cycle. And because they are created on separate places, it becomes kind of confusing. But let me see if I can find the function. Show. That function, so they use a method called index rendering, which is pretty much you find the index positions of the things that you want to render, and then you send the index position instead of sending the data. So you create a buffer that has the data of the actual points that are going to be drawn, and then you create another buffer which is going to contain the texture coordinates, and you're going to send obviously on the same VAO, which is a vertex array object, which is going to contain the state that you're going to send to OpenGL to render the thing. So after you set up these two buffers, you set up another buffer which contains the indices for each one, each point, and each texture coordinate that you're going to render one at a time. And this is going to bring me to another problem that I had after this, but I think I'm going to talk about after I go over this, which is the order that you render the points matter. So if you render them clockwise or counterclockwise, it's going to change the way that OpenGL deals with them. And I suspect this is one of the reasons I had a problem later on. But pretty much the way that you append the indices to create a vector, to create the buffer, the index buffer, for OpenGL to render is going to change the way that OpenGL does things, I think. Because it either is going to view as counterclockwise or clockwise, the way the order of the points that you're rendering. So here they do a bunch of stuff to initialize the default shaders and the default image that they use if you try to render something without creating a custom shader. You just use the default one, so they have a bunch of functions. This RLL load texture is the main one that is going to be used to create the texture based on the OpenGL functions. And I think here is going to create the code for the default shaders, which is just creating a model view projection matrix and then multiplying by the vertex position. And this translates the point into 3D coordinates because the projection matrix is going to contain the information of the near clip plane and far clip plane. And there's going to be, which is another thing that I highly recommend to read this. Specifically, this one is very well. It's probably the best article I found so far that explains this from fundamental principles. But it pretty much has, the matrix itself has some calculations to to normalize the point. So it gets all points and it's kind of like shrinking them into a range between 0 and 1. Because the final positions have to be in normalized device coordinates, to go from -1 to 1. Or raster coordinates, which is 1 after the normalized device coordinates. It's kind of confusing, but yeah. So you send this, you multiply this matrix based on the view matrix, which is the matrix that holds the state for the camera. And then another matrix called the model matrix, which holds the state for the model, which is the local object that you are creating. So you're just translating different coordinates, so you can have the final overall road coordinate for the object. So each matrix stores a specific state for each thing, and the reason why it's like that is because then you can translate and rotate and can store the states on the matrix itself. And this is the simpler version that I was talking about to render images. You just use this texture, and then you don't use the distancing from the SDF, and then you just use these other variables here that you're gonna set later on, the uniform variables, and these are actually the variables that are gonna decide what color the final thing is gonna be. And this one, the fragged X coordinate comes from the vertex shader, so you set up both the positions data and the fragment coordinates data on buffers from OpenGL, and then you send them both to the vertex shader with the in thing, or with the out here. And because it's out, then the OpenGL is going to understand that this is going to be used on the fragment, and then here we have in. But I think that stuff doesn't matter. Obviously, I put a bunch of... so this is... I don't remember exactly at what point, but they do this a bunch of times because the way that this is the main function that is going to render the things to the screen. And they do this on a bunch of different places because the way that they render things is based on limit that they put and some amount of memory or something like that. So at some checkpoints, they have to see if the limit was reached, and then if it was, then they flush they render everything and then they reset the values. But this is pretty much the main rendering cycle from Raylib, from their batch rendering system. And then here there is some stuff that is for the buffers. So they're setting up the buffers on the rendering cycle. And this is the stuff that I was talking about. So this one is going to be the one that is related for the positions that are going to create the quads. And this is why it's 3 times 4 here, because it's 3 floats and then 4 points, I think, for quads. And then this other one is going to be for the texture, and this one for the color. This is one difference from the way that I'm doing, because I'm using a uniform value instead of sending like this, but they are sending the values of the color along with the other values to the vertex buffer. And then this one is going to be the one that contains the indices. So this was the first thing that I was confused about, because they are setting the values here based on this thing here. So this is the function that actually tells OpenGL what data is supposed to, what data is OpenGL supposed to use whenever you call GL draw elements or draw array elements or something like that. The function pretty much that is gonna tell OpenGL to render based on indices, which you're gonna call in the main rendering cycle. Once you call that function, then OpenGL is gonna look for the place that you set up the buffer, the index buffer. And you do that by passing this flag here. And then here, this is supposed to be the data that you send. And I was confused about because on the rendering cycle, they don't have anything that builds the actual indices, which is kind of a annoying thing to do because you have to understand, like you have to think about how the quads are going to be positioned, how the triangles are going to be positioned on the final visualization. So you can think about what indices to put on the vector. Oh, but I think it passed. So it was probably this function here. Or maybe not. Pretty sure I put the boundary there, but maybe I removed. I don't know. So I might have to go again to find the function that's. Or I think I wrote down here just so. I think I didn't wrote the name of the function. But this is another point here that's. So the way that they set up the default matrix that they are going to use is based on this function here, which was another thing that was kind of confusing to me. So by default, I think they are going to use a orthographic projection matrix. And the example that they use, I think, I'm not 100% sure, but I think is because I tested the two different matrices. So what I did on, I think I erased the code. But I pretty much step over this, and then I got the values for the matrix that they built here with this one. And this seems to be the final one that they use on the rendering cycle for this example. So I just copy the values of this matrix to try to recreate the visualization. So I just got these values here, and these values are definitely different than the perspective projection matrix that I have on the other project. So what I think is happening is that by default they are using an orthographic projection matrix, and then when you try to use a perspective projection with the same example, it doesn't work. The text doesn't show. But then if you use these values here, it does show, but it only shows on a range of 1 from whatever z position you have, which I think is something related to these translations that the matrices do to get the final position. And that's the reason why I went back to study this stuff again to remember how it works. But I'm still kind of, I don't know for sure why this happens. I think it has something to do with the thing that's, because on the perspective projection, there is some calculation on 2 of the positions there of the matrix that are going to convert the point. They're going to do linear interpolation, which is pretty much finding the z points, the z value of a point. There's going to be obviously between the z near and z far clipping plane, and then dividing that by the overall distance, I think. So they find the distance from the point to the z near, and then they divide by the whole distance. I think that's what's happening. And then because they do that with all points, it's just going to normalize the points so that all the points are going to be between 0 and 1. And I think that this calculation is probably different on the orthographic projection. So that's the reason why, if you try to do it with the example that they give here, but you try to use a 3D visualization, which uses a perspective projection camera, what's going to happen is that the text is going to show, but it's only going to show on a range on a range of 1 from whatever the z position, initial z position that you put on the text is going to be. So let's say, for example, they put the z to be 0 on the text, then it's just going to show from 0 to 1 or 0 to -1, something like that. If you do it like this, and then any other position, the text is just going to disappear, which is very confusing. Because this was one of the main problems that I was having, is that I thought I was doing everything right, but then the text wasn't showing because of this. I think I skipped the function somewhere. I'm gonna try to go again. because I probably removed the some of the breakpoints. Not really sure if it's even worth it. I think it's on this RL init here. But pretty much I think it's not even worth it. So pretty much they have a function that's gonna initialize all the values of the buffers, which are the values that I showed there that they use to build the buffers later on the rendering cycle. So they initialize these values that are gonna contain the actual data in a function in the beginning of the execution there. And that function is gonna contain this cycle here. And this is the cycle that they use to build the indices for drawing the quads. So they just do a massive array. This buffer elements is gonna have, I think, 8,192 or something like that. The elements, or is an int that, and then it's gonna be times 6 because it shoot triangles for each thing. So they just create a massive array, and then the indices for the quads are gonna be always the same because it's a quad, obviously. So that's how they built the data they're gonna use later. I think I'm gonna show after I show this, I'm gonna show on the project that I was doing there. Like I said in the beginning, it's a lot of stuff to think about, so. So I guess I'm just gonna go over this one, to see if I can catch the function there. But it's obviously not on this one, but I want to show how it works to create the image. So this data here is going to be the data from the file. I think in the beginning is going to be the data for the default font that they use, which they have as hex addresses there, I think. So the default font, they don't use a TTF file. They just put the code here somewhere. Then you bind you clean up you free any bindings. You bind it to 0. There's a bunch of nuances about the filtering and the way that the OpenGL is going to interpolate values and it's gonna clip the image as well, but I'm not gonna talk about that. So all this stuff here is related to that, and there's some stuff about filtering as well. But this creates the image, and the data that they're using here is related to the overall font atlas, which is gonna be the entire image with all the characters. So it's pretty much an image like this. So the entire image has all the characters. That's the data here. And this MIP map is just a technique that you can do to maintain the resolution of the image across different scales. So the way that it works is that you create several different images that work kind of like a funnel or a pyramid, and each image has different sizes. In my case, and on this example, they only use one MIP map, but I think you can use more, obviously, based on the code here. So it's just generating several different images, and I think that the way that it works is that once you scale, it changes the image that it's using to render. But I don't know really well how it works. I don't think I'm gonna focus on that much. But this is the main thing that creates the. So one of the confusing things is that it doesn't create the image. The final image is the same as creating a normal buffer for the position data. You're just creating a place in memory that OpenGL is going to use to extract information from. So this is not the final image that is going to be shown there. The data is related to the font atlas, and this just creates the space in memory for the image. And then the width and height are the width and height of the overall atlas, font atlas. So I think I can go back to the other function. Pretty sure I'll look into this one as well. Trying to see if I can find the function that they create the stuff in the beginning. Yeah, I think it's this one. So this is the function. So in this function, they're gonna create the data that they're gonna later on use to create the buffers on the rendering cycle. And this is the stuff that I was showing there. So this creates the data for the indices, this loop here. So this is in the very beginning on the RLGL init function. I don't remember, I think it doesn't go, or maybe it goes over this. So it just sets up everything in the beginning as well. They do this probably both. They definitely do it on the rendering cycle, so but I didn't remember that they also do it here. To generate all the buffers here. And so now I think I'm gonna run over. So that's all the stuff that I want to show. Is in the beginning they build the data here, and then later on they're gonna use this data that they built here to build the buffers on the rendering cycle. This has this stuff here that I explained. And this is the function that is gonna, so you pass this is another problem that I had with the debugger, but it's something that I'm not 100% sure yet, which is how to deal with the relative paths on the final executable. But depending on the way that you set up the VS Code debugger, this can mess up. So the example, they had a relative path, so that's the reason why. And it makes sense for them to put the relative path because they don't have access to your system, obviously. But based on whatever the final executable is going to be, the relative path might break. And if it breaks, then the data for the file is going to be null. And then it's not going to throw any error. It's still going to render, but it's not going to be the correct way. So if that's happening, then you have to put the absolute path to the font. And this pretty much just reads the file, and then it's going to store the file on that data structure, the information for the file, which is the TTF file that contains the Bezier curves for the characters and the other information. Then they create this struct, which is where they are going to hold the information for each font, and they load the file. And this function is going to use, if I remember correctly, STB functions that are going to parse the data, which is this. You're getting the data from the file here, passing the data here, and then based on this function, it's going to store this information on this glyphs. Glyphs just stands for characters, so it's pretty much the same thing. It's the image of a character. So this is the one that initializes it extracts the information from the file data and puts on this data structure here. And this is going to get the metrics for each glyph, or for all glyphs. I didn't dive too deep into these other functions because obviously I was trying to make the other stuff work. Let's create these tables here. And this is just extracting the information that later on is going to be used to create to extract the correct characters and create the final image based on the points in the texture coordinates. I think we're just gonna go over this. Maybe I should probably save this. Oh, I think yes, I have saved here. So just this information here. So that's what the advance and the other stuff there descends. It's just this information here that you have to use. And this is one of the annoying things about rendering tags, is that you have to think about how all these relative positions are going to be, and then render the points based on this stuff here. So the point count is the amount of code points. The code point is just a way to say the UTF-8 representation of the character. So the way that UTF-8 works is that each character is just a symbol, and the symbol based on the agreement, which is the UTF-8 agreement, represents a code point, which is just a fancy way to say a number or a place in memory, something like that. And yeah, so each character is just a number by convention. And then it's gonna loop over the count of how many count points you want, and it's gonna create the extract information for each character based on these other STB-T functions. So there is another confusing thing here that I wish that they change on Raylib, and I wanna see if I don't skip this. I think it's on the next function. Yeah. So I'm just gonna skip this one. So after they extract everything and hold everything here, they pass to this other function to generate the images, which is just gonna, based on the glyphs, is gonna create the rectangles or store the information for creating the rectangles, which is gonna be each quad for each character that you're gonna draw. So this is the main function that does that, and generates the final atlas thing, the information for rendering final atlas. So on this function here, I think that there was something very confusing. Maybe it doesn't make that much of a difference for people that are using the library because they're not going to look at the source code. But I think it's just a small thing that shouldn't be a lot of effort to change. So I just went off the example, but there are two different back methods here. I didn't really dive too deep into this, but just different ways to extract the information. So I just went off the example that they had there. I'm probably going to spend a bunch more time to understand the rest of the nuances that I still don't understand. But yeah, so the example, I think they use the back methods one. And then these are the two functions here that were also confusing because the name of these functions is exactly the same name as STB TrueType uses, but they come from a different file, which is a file that I think that people from Raylib created, which is this STB rect pack file, to allow a different or a more up-to-date way to extract the information for each rectangle. But because they use the exact same name as STB TrueType, I was using the STB TrueType function, and obviously, like, wasn't giving me any warning or error because the function exists. So yeah, what I think they should do is probably change the name of this. I'm not really sure why they didn't do it like this. So change the name of this function so that it has a prefix or something like that. And these rects here, I think is these ones. These are the data structures that are going to be used on the main rendering cycle once you are looping over the tags and the functions that are actually going to create the points and the texture coordinates to render the tags. This is the main data structure that is going to be used to calculate the x and y and width and height for the coordinates. So they're just calculated based on this other stuff here. These rects that come from STB, from this packing method. It's based on the glyphs, which is each character, the image for each character, width and height, and the padding. And then creates a context here based on these rectangles. And then creates this final rects based on this other stuff. And there is, I think it's at the end there that makes this equal to, which is another confusing thing. I remember thinking about this at this part here. So this is was passed on the main one. So this is a pointer to a pointer that they pass on the main function from outside. So these are, I think, was either the result, I don't remember really well, but it came from the other function, obviously, and they passed and they update the values of this, which is going to be on the other data structure that they use to hold the information for the fonts. So at the end here, they destructure this and they make equal to the recs that they create here. Just gonna pass this. So it's from the fonts SDF here. So these recs here are going to be the same that it was created inside of this function here. So they are holding the information for each rectangle inside of this data structure, which later on they're going to use to create the characters. This is the function that I just showed that is going to create the image based on OpenGL functions. And they unload everything. I think I'm not going to show this, but it's pretty much a bunch of functions to load the shader. Oh, I got the STF from them probably. So they hold this somewhere on the rec samples and the resource shaders and then SDF. And I think I just copied the code from them for the shader. Which is the code that I showed there in the beginning. Has the sampler and the calculation for the lengths. Yeah. So after they do all this, actually now that I think about it, maybe I'm not really sure if the example is going to be working as it is, but it doesn't matter because I only want to show the functions. But this stuff here I put later on because it's how Raylib renders the 3D visualization. So the camera for the initial example of the text is not necessary, and the update camera function is also not necessary. So it might not render. Yeah, it's probably not going to show the text now because I have these other functions here, and then this begin mode 3D is also for the 3D. But this stuff doesn't matter for what I'm trying to do. So just gonna show the functions. So this receives the font, which is going to be the STF font that they initialize there. She contains the information, which is the rectangles that I just showed. And then this is going to be the size of the overall text. So it's looping over the size, and then for each, so it's extracting each character based on this thing here, and then passing this stuff, which I don't remember really well. But this pretty much just is going to get the next code point based on the text. So just going to use the text to figure out what code point is, it's translating the. I'm not really sure if it's byte information from the text to UTF-8, to a UTF-8 code point. It's just getting the UTF code representation of the character, and then it's getting the index of where the code point is located inside of the font that initialized there in the beginning. This is something that I can probably change there because it does this twice, but they probably have their reasons because the way that they structure all the functions, but for my case, I think I can do it only once. But it's just looping over the glyph count, and then it's trying to find the value of where the code point is stored at, which is based on the glyphs that I show there in the other functions that it creates. So it used STB true type to get the information, and then it stores on these glyphs, and then on this loop here is gonna get the value. It's gonna filter which code based on the text, got the code point, and then based on that code point, it finds the index of where the thing is. Then based on that, if it is a space, it's just going to change the offsets. So if you put new line on the text, which is the thing that I use to create the new line, obviously, it's just going to create the you're just going to change the offsets here. So the offsets are used to move the, it's kind of like you have a pointer and you're drawing one image from 0, then you draw the rectangle, and then based on the offsets, you're going to go to the right and to up and down to draw each character at a time. So this is the reason why it's 0 here, because then once you reach the end of the line, it's going to be 0 again. And the line spacing is just the distance from one line to the other, the offset here. And it's going to pass this to this function here. So this is the part that the example that I show helps a lot to clarify how it works. So the position here is the position outside that you send, which is going to be like the relative position on the road coordinates where the text is going to be drawn. So you can either start drawing the text, for example, on the 0, 0, 0 coordinates, or you can start on the 10, 5 coordinates, which is another place. And then all the other coordinates are going to be relative to that point. So that's the reason why it sends the position here, is just the beginning position. The offset is going to be based on these rectangles that in the index, it gets the width for the character. And then this scale factor, which I think is arbitrary, they decide. And the spacing is also arbitrary. And scale factor is based on the font size, which they calculate here. Which is also based on the font base size, which was extracted from the TTF file. So it's doing the offset based on that and sending this value to this function. Then it gets, this is the part that I think that is kind of redundant, but maybe there's a reason for them to doing like this. But for my case, I think I can probably remove, because they're calculating the index twice. But then what they do is just create the 2 different rectangles, and what the rectangles represent is the source rectangle is going to be where on the font atlas you're extracting the information from. So you can imagine and have this. The source rectangle is going to be the rectangle that wraps one of these symbols here, which is going to give you the character. And this example really helps understand that. So the source is like this here. So imagine imagine all of them is a font atlas, and then each one of them is a character. So depending on the coordinates you have there, it's just going to change whatever character you're rendering. And the destination rectangle is the positions of the final quad that you're going to have on the visualization. It's going to be these positions here. And the width and height, obviously. So this is the final function that is going to render, that is going to create the points. So send the texture, the source, and destination. And this other thing here is the origin, which I didn't use, but you can see on the example there that based on the origin, it changes the final thing that is going to be displayed. But I didn't see a point in changing this. So this is the final function that they're going to use to render everything, or to create the points, which is something that I changed as well from the way that I'm doing, because I didn't like the. I think the reason why they did it, the rendering system, the way that they did, is because they were working with an OpenGL version that is older, and then on that way it was a different way to render everything. So they use different functions and to render stuff. But this top left, top right, bottom left, bottom right are the coordinates of the final quad. So it's obviously 4 because you're generating the final quad based on the points you're going to send here. So yeah, the default case there on the example, the rotation is going to be 0. So this calculates origin is going to be 0 in my case, but is these values here, we're going to change the what's displayed. The top left, because it is inverted, the image is inverted because of some transformations that happen, then, or maybe I'm not really sure. Yeah, but I think that it starts from 0 and then it goes down. That makes sense. But maybe I was confusing. Maybe not. Maybe this is right. So like, top left, you can imagine that's 0, 0. Then top right is just going to be that position plus the width of the character, because this is it's calculated based on the other function, which has the offset and has the other information that comes from the rectangle, which was extracted from the file. So just the width of the character. And then y, so bottom left is going to be y plus the height. It is inverted, so like you can imagine that it starts at the top, so it's plus the height because it is inverted, so plus the height is going to be to the bottom, and not minus. And then here just plus the 2 because it's then bottom right. And then here on these functions here are the ones that they are going to store the coordinates. So these are all text coord 2f is the normalized texture coordinate. So you divide by the width on the x direction, and you divide by the height on the y direction, because they're trying to collapse the value into a range between 0 and 1. Because you're going to send these points into the sampler, which is the final code there on the fragment shader that is going to be used to extract the information from the font atlas. And then the positions is just going to be, and this is this is, I think, the main problem that I had. So the reason why the text wasn't showing for me on there's two reasons. One is the thing that I talked about before about the orthographic projection, because I think that the way that they built this stuff was for orthographic projection, but maybe not actually. But the main reason, I think, is because based on the way that they are putting the points here, the way that the final text shows up is inverted. So if you do just like the way it is here, what's going to show is the back of the text, not the front of the text. And because I wasn't creating the points for the back, then even though everything works fine, nothing shows on the screen. And it took me a massive amount of time to figure this out. But luckily, on the other example, they have a variable, a Boolean variable that tells you whether or not you want to render also the back side of the text. And then if you put that, it shows the text inverted in the beginning. And I think that probably one of the main reasons, but I'm not 100% sure, is because of the order that they put the points here. And the order mattered because of the stuff that I was talking about in the beginning, about the way you build the indices buffer, which is going to be the way that what OpenGL uses to extract the information for building each point in texture coordinate. So it's reading you can imagine that it's looping over the indices vector that contains the information for the indices. Then for each index, it's just going to go to the other buffers. It's just going to search the data for those indices. And then it's going to render that point first. And then it goes based on whatever the order of the indices you have there. So based on that order, it's either going to be clockwise or counterclockwise, the way that it's rendering everything. And this matters because of the edge function. And the edge function is just the calculation of the difference, I think, in positions from the points, that is going to allow OpenGL to clip the triangles that it builds on the final part of the pipeline. So, or I think maybe the edge functions happen on the geometry shader, but also scratchpixel has a very good article about this. I don't remember exactly where, but there is an article that talks about this. I think it's something, probably this one, the rasterization one. Yeah, it's on the rasterization. So the reason why the GPU renders triangles is because you have to create a geometry from the points in order to be able to clip, to decide what you're going to clip, and to decide what triangles are part of which squares, because each pixel is going to be a square, obviously. So the simplest geometry you can do is a triangle. So because of that, you use edge functions, which is just the calculation of the differences in positions, to decide what triangle you're going to clip and how you're going to color each pixel. And because of that, then the order in which you put the points matter, because it changes the way that this edge function works. And I think that there's something that I wrote down here as well. I forgot the name. Winding direction. Yeah. So the winding direction determines whether a triangle is facing camera, front facing, or facing away. So I think that I'm not 100% sure, but I think this is the reason why based on the example that they're doing there, is showing the text inverted because of the order that they are putting the points. And then because of that, if you try to render the text on a 3D visualization, it doesn't show because it's a different transformation than the orthographic projection, which probably clips the text on different positions and also shows the inverted text. So I'm just gonna step over a couple of them to show how it works. This is just gonna set the current texture, and this is the thing that I was talking about that I didn't like that much. I think the reason why they did like this is because it's an OpenGL or older OpenGL version. So they put this stuff on these data structures, and this is the final one that is gonna put. And this data structure is going to be the one that is going to be used on the final rendering cycle there to render everything. And so this stuff here is going to hold the texture coordinates, or the position, not the texture, the positions. This holds the texture coordinates, and this holds the color. So it builds all these points based for each character based on the rectangles here that I explained, and the recs based on the TTF information that has the width and height, and the offset for each one, which is the spacing between characters. So I think the final thing is probably the render batch. So it builds all the points based on and holds them on that data structure. Then after it does that, I think that is a problem because it's probably gonna be here. No, it's either on. I think it's on end shader mode that they have a call to render everything. But because I changed this, it might be fucked up now. So on this one, they check to see if you have to render, and so they build all the points on the previous function, and then this is the main one that is going to flush all of them and render. So the main rendering cycle. So the vertex counter is the amount of vertices that you built based on the characters there. Not sure if I can. I think if I, yeah, it's gonna be 80, and it renders everything at once. So here it builds the buffers for each thing. And this is the matrix that I was talking about. So on this one, it seems that they use the orthographic projection on the main example. And then they convert to floats. So this was the one that I copied there to see in the beginning. Then they set the color and the diffuse or whatever. So they bind the texture, then the mode is going to be RL quads, which means that they're not going to use this. So the GL draw arrays is used when you want to draw stuff based on a normal buffer. And the GL draw elements is whenever you want to draw stuff based on index buffer, which I believe is the one that they are using. And then they do this calculation here because of quads. So it's divided by 4 because each quad has 4 points, obviously. And each thing has 6 points, which is 6 triangles, and then the number of quads is going to be the division by 4. Just multiply by 6 and divide by 4. And this is just going to be the count. It actually doesn't matter that much. It's obviously better if you can do the precise, but I think it doesn't matter if you do more than you have there, because then the other points is just going to be just not going to draw anything. Just the amount of draw calls you want the OpenGL to do. And It's going to do that based on the stuff that you set up before, which is all the buffers and the data that I showed there in the beginning, the way that they set up the indices. So the main thing, the main point is that I believe that the reason why this doesn't work on the 3D is because, for two reasons. One is that they are using orthographic projection, and the other one is probably the order that they are putting the points, but I'm not 100% sure. Is this winding order? But I am 100% sure that the other example that they show there, it renders the text flipped. It renders the back of the text, not the front of the text. And then you have to flip it to show. So maybe I'll comment this out and I'll show the 3D example. Or I think I don't need to, actually. Just gonna show the stuff that I did and how I translated everything. And there's also the final thing that I wanna explain. So I think I'm gonna explain this on the project that I have there, and then explain the whole project. I'm not gonna show the 3D example because it doesn't matter that much. It's just it's gonna be very similar. So, but then I got the functions from that example. The only difference is the way that they build the final functions there. They draw text code point, which they use different values. So the thing is that I thought that the reason why this one might be working is because on the example here, they instead of increasing y by the width or y by the height, they increase z, and this makes it work. And then once you increase y, it doesn't work. But then I think if you put the flag variable there, then it starts working. So now I'm not really sure if I should. Basically, what I did was just create a class, and so I'm gonna show billboarding first, which I got from this video here, this guy. So billboarding is just so after you render the text, then the problem you have is that the text. So the first problem is that you're rendering the back face, and the text is flipped, so I have to flip the text. This was one issue, and the other issue is that when I was changing the camera, then the text was rotating or fucking it up. So what you have to do is a technique called billboarding, which is just making sure that the quad is always facing the camera, no matter the position of the camera. And the way to do that is very simple, and I saw from that video, but the problem is that if you have a situation like I have, where you have to rotate and billboard, then it's slightly different. But the way you usually billboard is just by putting this plus here. And the model view is the matrix that is going to contain the... It can either be the camera view matrix, but in my case, it's the camera multiplied by the model already. So these values here of the camera matrix are going to be the right vector and the up vector. And then you use those values to multiply based on the position you're getting. So you're pretty much aligning the position with the camera based on this multiplication here. But if you do it with the plus sign here, then the problem is that the text is going to be inverted. So if you want to flip, you just do the minus sign. And the minus I got from ChatGPT. So I think I'm going to explain how what I changed there. So basically, what I did was just pass everything into a class. And I've put this project on GitHub as well. So this is the repository. So if anyone wants to see how it works, I think that the way that I did here is a lot more simpler to understand, to be honest. But I got this camera from another project, which is the 3PP. So I initialized the camera here, aspect ratio, I think the field of view, and then the near and far plane here. Then I initialize this class, passing the font path and the path to the fragment shader and the vertex shader. Oh, and this stuff is on the stuff for the Billboard is on the vertex shader. And there you do. So here's pretty much the same thing here. Create the program, and then I need the fonts. This is the function that I showed there. It's gonna load the data. These functions are just copied from Raylib. So got the information for the tags, and then I'm putting this stuff on inside of the class. The main difference is gonna be on the functions to render, which I got from the other example, and then I changed a little bit. So after I need the fonts, I have other two functions here that I did on the other project. This one, it queries OpenGL to get all the uniforms, and then it caches them on a map. So you're just asking OpenGL based on the function you have on the fragment shader and the vertex shader, what uniforms are actually being used on the final calculation for either the fragment color or the gel position. So I'm getting all the active ones, and then I'm storing them on this map. And here, same thing for the attributes, just querying OpenGL and then storing all the attributes that are used based on these functions. Oh, it's another one. Then this is the main one that I'm building so this is the initial position, so the way that I'm doing now is I always draw the text on the 0 position first, and then I translate based on the model matrix. It's a lot easier. I think this was probably one of the problems with the other one, is that but maybe not, I'm not sure. I guess I can test that later, just see. But I think that's just easier to do. So you put the 0 point as the beginning, and then this function I got from the other example. So here I pass through to render the back of the text as well. And then on this one is pretty much the same as the other one. So it's looping over the length of the text, then gets the code point, the index, and then this one is gonna generate the final text. So, but on the example on the 3D, they are putting this offset on the Z position, and not the Y. And this is one of the reasons why it was rendering, and then that I was having a problem, I think, to render. So I don't know really well. Maybe they did it like this because of the same problem that I faced there. I'm not really sure. But I think it's just better to do it on the Y position. So I think that the main reason is the stuff that I talked about before, which is not rendering because for some reason it renders the text on flipped. So the other one is pretty much the same. Just getting the offset here based on the racks. The spacing is the arbitrary thing, and the scale is based on the font size. And the code point is the current character to be rendered, and this backface is the flag variable that's gonna allow. So I think I'm gonna spend more time studying this as well to understand how the points work, because it's kind of confusing to think about why does it work why does putting the other points create the back of the text? It's kind of confusing. And I think the fundamental thing to understand, and that I probably have to spend more time as well, is the relationship between GL position and texture coordinates. But I think that the image there is very good for this, but it's still kind of confusing to me to think about it. So based on that, then the offset's going to be done based on these positions here. So this is one of the differences. And the other one, I think, it does inside the loop. But maybe it's the same thing. Maybe the only difference between this one and the other one is that this one was increasing on the Z direction. So maybe the other one, I didn't test to see if the other one is going to work. If I try to put these other points, or if I try to flip. So I guess I can test that later. But I think I'm not going to do that, to be honest, because I'm pretty happy with what I got now. But it's pretty much the same thing. The source rectangle is going to be the how you extract the coordinates to extract the information for the character based on the font atlas. And then it's going to normalize here. So it divides by the width and height to get the normalized coordinates. And then here, instead of doing putting on the data structure that they do there, obviously I'm just using a vector and then putting them on a vector, and then later on I'm going to use this these vectors here to create the buffers. So it starts at the top, obviously. It's pretty similar to the other example, and then here the bottom left is just going to be the height because it's inverted, and then it generates the 4 points based on these positions here and the texture coordinates. And then here is the thing, if you pass backface, these are going to generate the back of the text. But I haven't spent a lot of time to understand exactly how it works. And I also am gonna have to spend time to understand this winding direction here and why is it working. Because it would be better, obviously, if the text was rendered at front face first, because then I don't have to flip there. But I think it doesn't make that much of a difference, because you still have to do the calculation anyway to do the billboarding. So I think it doesn't matter that much. Yeah, and that's pretty much it, I think. So after you do this, it's gonna be pretty similar. So this is the main thing that is gonna generate the points for each character and the texture coordinates. The image buffer is the same. I just got the functions from Raylib, and is the functions that I call here on this init thing. So this load texture from image is gonna be the one that generates the buffer for OpenGL that contains the information for the image. Then generates all the points based on the vectors that I have on the class here. It's these vectors here that are going to contain everything. So after I generate all the points, I call another function that is this one. That this is just the same from Raylib. Just generates the indices based on the vertex size. This thing here, I'm not 100% sure yet, because I tried different values here to, for example, divide by 4 to get the exact amount of indices, but I think that like they didn't work very well, so I didn't spend a lot of time thinking about this. The here is going to increase by 6, so I think I'm getting more indices than the text actually has. So, but I think I tried dividing by 6 as well, and didn't work. So maybe I'll experiment later. But this builds the vector that has the indices for creating the quads. Then this one is going to create the buffers. So based on the data that I built there, it just creates the buffers here. And I create outside of the rendering cycle, because the downside of doing that is that if you change anything, then you have to update. But then later on, I think you can just put, like, I can just put an update function and then change this, but I think this is fine. So you create all the buffers once, and then you just call the draw call in the rendering cycle to use the data you put here on these buffers to draw. And this is pretty much the same as Raylib is doing there. And then here you're just using the program, because you have to use call use program before you set any uniforms, which is another annoying thing about the OpenGL, because it doesn't throw an error, I think, if you don't do it. And then this is just setting the color based on whatever color I passed there to initialize the class. the color that is going to be set on the shader. So it's going to multiply the final alpha channel that I get from extracting the information from the image based on this move step. So it gets the multiplies the alpha. This diffuse color is going to be the final color, which is based on this fragment color here and the opacity. Later on, I have to set this opacity as well, but I think it doesn't matter that much. I think that's pretty much it. And then I was rotating, but now since I'm able to do that on the shader, which I'm pretty happy about, then I don't need to rotate here. So after you do all this, initialize the class, I set the projection matrix on the shader based on this function here, to be the camera projection matrix. Here to show this, there is a make projection function, which is the one that is going to build the matrix. But I think that scratchpixel article is very good to explain this. It's going to be make perspective, I think. Yeah, this. So it builds based on this here. So these values here are just values that are from, I believe, the near plane. So as far as I understand now, the way that the model that I have in my mind, so the way that you imagine is that the eye of the camera is outside of the screen. It's like, imagine you are the eye, then whatever shows on the screen is the near plane. And what creates the effect 3D is the far plane. So it's creating a pyramid from you to the far plane, where the creation of the image happens on the near plane. And then you get these values here, which are coordinates, I believe. I'm not 100% sure, but I think it's from the near plane, that are based on the angle you have from the field of view, and the distance between the eye and the near plane and the top, and other stuff like that. I don't remember the nuances very well, so. But it's just getting these values of these coordinates, and then it creates the final calculations you need to have on the final matrix based on these values. And because you're putting all these calculations inside of this matrix, it's gonna automatically change the visualization to give the effect of 3D. So this D value here, for example, holds the value of the W. It has to be homogeneous, because homogeneous just means it's a 4x4 matrix, because the W is gonna hold the value of Z, and the way you get the illusion of 3D is by dividing everything by Z. So you need to hold the value of Z on this W so that OpenGL does the perspective divide, which is just dividing by Z, the X and Y and Z coordinates. And the other ones here are the ones that are, this B and C are the ones that are gonna normalize the coordinates. And this is just based on the near plane, I think. Yeah, I don't remember really well. Just coordinates. Maybe this is the far plane. And then yeah, this X and Y is based on the focal length, I think. So they are used to take into account the focal length, which is the angle of the camera, which is pretty much the scale. So the article talks about it. It's probably the best article, to be honest, that I read about this, is this one. So I set there, and the way that I set is just based on these functions here. So I think I use ChatGPT to help me with this. So use the program first, then you find on the map that I did on the beginning there to cache the uniforms based on the name I passed here. So this is going to be the variable inside of the shader that I'm setting. It's going to be the projection value here. So you get the location of the variable, and then you set with the new value, which is the matrix for the camera matrix that I have there. And then I think that the final thing is just the rendering cycle. And so I call this update matrix. Maybe I think I don't need to call this anymore, because this one does it. Or maybe I do actually. So what this function does, yeah, because on the other project I have scene, so scene is gonna update everything. But what this function does is just, it's gonna recalculate the values of each matrix based on whatever properties you have inside of the class that might change the overall value. So it composes the local matrix that contains the state for the object that you're creating based on these values that holds inside of the class. The position is where the object is located, is the local position of the object. The quaternion is it holds the state of the rotation, and the scale, the state of the scale, obviously, and then it composes based on these values. So this just creates another matrix that is going to have the final one. There's going to be based on these values here. Where is it? So after it does that, then it multiplies. So if this object has a parent, then it multiplies by the parent, and then it stores the information on the matrix world. So this is just the state of the local state of the object. So it holds the whatever happened to the object on its relative coordinates, and then this matrix is used outside there to multiply with the inverse of the camera matrix. So because you update here, you multiply here. So it is the inverse of the world because you're trying to translate, because the camera is just it's as if it's a normal object on the scene, but it's going to be used to visualize everything. So I think the video, on this video he explains probably a lot better than me as well. But it's the inverse because you're trying to translate from the local coordinates of the object into the world coordinates, and then this is going to be the final model view matrix there that is multiplied by the projection that I set there, and then that finally is going to be multiplied by the positions that you're setting based on the rendering cycle, which is based on the buffers you have there. And so set the value of the model view on the shader on this function, the same as the projection there that I showed. And then the final is going to be this one, which is just uses the draw elements to get to render the indices based on the index buffer that you set up there before. And you have to put this bind buffer VAO here because the vertex array object is the thing that holds the state. And you also have to call this so OpenGL knows what image the fragment shader is going to use, which comes from that function there that I showed. So this texture here, you have to bind. So you first you tell OpenGL which active texture it is, and then you tell it what image that you created before. So what buffer of data OpenGL is going to use to render, to render pretty much. So what image is using here on the sampler today. And I think that's pretty much it. Yeah. So this is the final one, and then this creates the text. So I'm pretty happy with this. It was very hard to make it happen, but it's working now. So what I'm gonna do now is just translate this into the other project that I have there. And yeah, so I think I'm gonna stop here. I'm not really sure when I'm gonna stream next, but so now what I'm gonna do is just translate all of this stuff into the other project that I'm building, and then try to incorporate this stuff on the other one, and then move on to the other stuff that I have to do.